So here we are, we're looking at the equilibrium between iron 3 plus, that is from iron 3 nitrate. It's a pale yellow compound, as you can see here, dissolved in the water. At this concentration, it actually appears almost colorless. We also have, right beside it, a solution of potassium thiocyanate, which contains the SCN- complex ion. It is also a colorless looking compound. When these two things mix, the iron 3 nitrate and the potassium thiocyanate, the iron 3 plus and the thiocyanate ion, SCN-, they'll combine to form a brown-red compound, iron thiocyanate, or iron 3 thiocyanate, which is the formula FeSCN2+. And as you can tell from looking at the little petri dish here, the compound is brownish red or slightly orange looking in color. We can demonstrate the reaction. We'll take in the top left-hand petri dish, we'll take a little bit of the iron solution. We'll put it in this dish, a big drop of it. And we'll take a little bit of the thiocyanate. Now this is going to be quite dramatic. Take a little bit of a thiocyanate. Now these two solutions are relatively concentrated, and so take a look at what happens when they mix together. So we'll put the two of them side by side. There they are. And now we'll get them to mix together by just sort of touching one to the other. And you can see that when they mix, you immediately get a reaction which ends up forming a bright reddish colored compound, the iron thiocyanate. At that concentration, it's blood red. We can dilute it with some distilled water. But even after filling the dish with distilled water, at that concentration, it turns into a really bright reddish brown color. This is used in some chemistry magic shows to simulate blood, actually, because it's such an intense brownish red color. If you dilute the solution, though, you add lots more water, you can get to the colors that we see in these four dishes. So these four dishes all contain the iron thiocyanate compound, much more dilute than the dish up here on the far left. Now, one question I've got for you right now is, how can we tell that these dishes, all five of them, the four light-colored oranges and the dark reddish-brown one on the far left, how can we tell that they've all reached equilibrium? What is it looking at those dishes that tells me that they have reached chemical equilibrium? If you're thinking because the color is not changing anymore, then you've got it, okay? The iron was pale yellow, almost colorless. It reacts with colorless thiocyanate and produces the brownish red iron thiocyanate. If the reaction was not yet at equilibrium, we'd expect either the solutions to be getting darker reddish brown as they make more of the compound in product form, or perhaps the reaction would be going reverse and they'd be becoming lighter in color as the iron thiocyanate decomposes. In fact, the compound is rather unstable, and if we sat here for half an hour or an hour, we might actually see that the compound is slowly decomposing over time. Okay? So we'll have to work relatively quickly when we deal with it in a quantitative way. What we're really interested in here is Le Chatelier's principle. Le Chatelier's principle says that when we have a system at equilibrium, like these dishes here, and we apply stresses to those systems, the systems will then shift. The equilibrium will shift. Will either shift in the forward direction, making more of the iron thiocyanate compound, or will shift in the reverse direction, destroying the iron thiocyanate compound and turning back to the colorless iron and thiocyanate ingredients. Now, because of the colors involved, we can easily deduce what direction this equilibrium shifts. If it shifts in the forward direction, it'll be making more of the iron thiocyanate compound, and so we would anticipate a reddish-brown color to get darker. If, on the other hand, it shifts backwards, towards the colorless iron and thiocyanate, then it would be using up the iron thiocyanate compound, and the reddish-brown color would disappear or fade out. Okay? So keep in mind that if you see a darker reddish-brown color, it means more of the compound is forming, and so the equilibrium is shifting in the forward direction. If the reddish-brown color fades, then it must be shifting in the reverse direction instead. We're going to apply some stresses to the systems at equilibrium. So, for example, let's take one of the dishes up here, and we're going to add some more iron to it. So I'm going to take some of the iron 3+ solution, and we're going to add some, increasing the concentration of iron 3+ in this dish. Now, looking at the balanced equilibrium below, can you predict what will happen if we add more iron 3+ to the system? Well, let's take a look and see if you're right. Okay, so we just added more iron 3+ to the system, and we see that it got darker reddish orange, darker brownish red. So that darker color is telling us what? It's telling us that there's more iron thiocyanate in that equilibrium, and so the equilibrium must have shifted in the forward direction. So adding more iron 3+ caused the system to shift forwards and produce more FeSCN2+. Again, because the color has stopped changing, we know that the system has reached a new equilibrium position. Now we'll take a dish beside it and we'll add some more thiocyanate this time. So SCN-, we're going to increase its concentration in that dish. Can you predict what will happen if we add more thiocyanate? Okay. If you predict it again, that we'll get a darker brown color. If you predicted that the reaction would shift forwards and produce more iron thiocyanate, then you are correct. Okay? So adding either the Fe3+ or the thiocyanate caused the concentrations of those things to increase, and the equilibrium shifted forwards to produce more iron thiocyanate, the brownish red compound, and come to a new equilibrium. Now we're going to perform a couple more stresses. This time I'm going to do something a little bit strange. We're going to add some silver nitrate. Okay? Silver nitrate contains the silver +1 ion, Ag+, and we'll just take a look at what happens if we add some silver nitrate to one of the dishes at equilibrium. Now, if you look carefully, you'll notice that there is a formation of a precipitate. Okay? There's a white precipitate that is formed inside the dish. I'm going to reach into that dish and give it a bit of a stir. And you can see as I stir some of the wisps of white precipitate. That white precipitate is silver thiocyanate, AgSCN. Now the question is, what's happening to the reddish-brown compound as we mix the solution? Okay, so we'll let that settle down for a moment. Do you see any evidence in that dish of reddish-brown iron thiocyanate? Neither do I. So it seems that when we added silver ions, Ag+, to this equilibrium, the iron thiocyanate disappears. What does that tell you about the direction of the shift? That's right, the reaction must be shifting backwards. Now, the explanation for that is a little bit more complex. I'll see if you can figure that out. So why would adding silver ions cause the equilibrium to shift backwards? In our last equilibrium shift, we're going to try adding some potassium oxalate. Okay, potassium oxalate contains a complex ion, C2O4 2-. And we're going to add that potassium oxalate to a system at equilibrium. Okay? So we'll add it to this guy here, which is darker reddish brown. I'm going to add some of the potassium oxalate. Now, as it dissolves, what happens to the position of equilibrium? You can sort of see it there, but I'll add a little bit more. Okay? what is the addition of oxalate, C2O42 minus, doing to this equilibrium? Is it causing it to shift forwards, or is it causing it to shift backwards? Okay, we'll give it a bit of a stir, and you can see that the compound, the reddish-brown iron thiocyanate, is completely gone. So adding oxalate caused this equilibrium to shift backwards, okay? Just like adding silver caused it to shift backwards. What would be the explanation for that? Now I've got over here also some of the solid iron 3+. Okay, let's see if we add some iron nitrate, which contains the iron 3+ ion, add it to a system at equilibrium. So we just pour some of that solid directly in there, and you can see that adding the iron nitrate also causes the reddish-brown compound to appear darker color. Now you might be thinking, but solids don't affect the position of an equilibrium. And you're right, they don't. But remember that nitrate salts are very soluble in water, so as the iron nitrate dissolves in water, you are increasing the concentration of iron 3+, which was similar to what we did in our very first equilibrium shift. Okay? So adding solid iron nitrate, the iron nitrate dissolves, and as it dissolves, you're increasing the iron concentration, and from the darker orangey red color, it appears we're making more iron thiocyanate.